All right, so let's start. Welcome to class, everybody. My name is Purvi Gupta. I'll be your instructor for this semester. Now, if you want to reach out to me, as I said on the webpage, the easiest way to get to me is via email. You can also drop me a chat message on Teams, and I'll try to respond as quickly as possible. I do come to the department once in a while, but my schedule is quite erratic. So if you want to drop by and say hello, make sure, just reach out and check whether I'll be there. Now, I don't want to, so by the way, if at any point of time you cannot hear me or you cannot see my screen, so I will be using my tablet, and it does happen occasionally that you don't see the shared screen. Please just turn on your mic and interrupt me or drop me a message on the chat box. When I'm usually writing on my tablet, I don't always see the chat box. Okay, so if you see that somebody else has posted a message, and just turn on your mic and interrupt. Now, I don't want to spend a lot of time talking logistics because we kind of have to repeat a lot of these points over the semester. So as and when it happens, we will discuss the logistics. But let me give you a couple of, let's start with a couple of points. So the first point is that on the Teams page for this course, on the main channel called General, I've posted a survey. I basically need to figure out who all of you are taking this course for credit. If you've already decided, if you've not decided, just say that. This is a little bit to figure out, what my TA is supposed to do. So please do fill in that survey. And let's also just quickly share the course webpage, which is definitely one resource that you should keep an eye on. Yeah, please interrupt if you have questions, but let me just quickly say a couple of things I do want to go over. So I have not announced the office hours yet because I first want to figure out when your tutorials will be, and I'll say something about that in a minute. The main things are the components of this course. So how are you going to be graded? There are 4 components. They're going to be quizzes, assignments, 1 midterm exam, and a final exam. Let's discuss the exams later. It's too early. Assignments as well. So I'll post the first assignment on Wednesday. So on Wednesday, I'll discuss a little bit about, how do you submit these assignments? What are the rules? Let's not waste time on that today. But expect the first assignment to arrive on Wednesday. Okay, and typically it will cover the material that I'm going to cover in this week. Now let's talk a little bit about quizzes. So the point of these quizzes is they're going to be short, and the idea is that I need to make sure that you're keeping up with the material. So it really is a sort of a week, the idea is the quizzes are not meant to prepare you for the exam. They're really to test whether you're following what's going on. And these will be held in the tutorial, and I will leave it up to the TA. So your TA will be Preetham Ganguly. You'll meet him next week. So this whole tutorial business starts next week. I see a message of bad network quality. So is it that you can't? Okay, it doesn't look like anybody said anything. Okay. Right. So, the reason why I want to make a fuss about this right now is that because your quizzes are going to take place in the tutorial, we have to set a time that works for everybody. So what I have done for that is I have set up a survey. This is on the channel called Tutorials on our team page. So there are 3 channels right now: General, Tutorials, and Weeks 1 and 2. Is there a question? I hear some background noise somewhere. Okay. So anyway, so the main takeaway of this entire discussion is that please go to the tutorial channel on our page. There is a survey over there. It gives you 6 time slots, and you need to give me your preferences for when you want the tutorial to be. If you are taking this course for credit, this is extremely important because your quizzes will take place during the tutorial, and that's also the time for you to actually do some problem solving. So we won't be doing that much problem solving in class. We will be doing a lot of proofs, theorems, proofs, things like that in class. Also, I will be posting the assignments on the Teams page. So everything will be available on the Teams page, but I'll keep a calendar over here. I'll try to update a calendar over here so you have a sense of what is coming up. Let me pause and see if there are any questions right now. If not, let me see if there was anything else. So yes, so there are two things for you to do today. One is to fill the survey about whether or not you're taking this course for credit. And the second one is to tell me when you would like the tutorials to be. There are 6 time slots available depending on Preetham's convenience, and you have to give me your preferences. So those are the main things. We'll come to the other things a little bit later. So let's kind of get started. I'll switch to my tablet, but before we get into the math, let me just give you a little bit of a sense of what the theme of this course is and where we are headed. So this is kind of, I mean, one of the I should also mention one more thing because I got a lot of emails about this. So Math 221 Real Analysis is a hard prerequisite for this course. Okay, so if you've not taken that course at IISc, then you can't take this course for credit. So if you wish to audit, if you've not taken that course, but you still want to audit this course, I have no problem with that. But to be a creditor, you have to have a grade assigned, a grade from your Math 221 course. Okay, so please be sure about that. All right, so let's talk a little bit about, what is this course about? What is typically a first course in complex analysis about? So Math 221 is where you, set up a very rigorous calculus for functions that whose inputs and outputs are both real numbers. Right. So now the point is that just as the field of complex numbers has certain advantages over the field of real numbers, it seems like doing calculus over complex numbers may hold certain advantages over doing calculus over real numbers. So the main objects for doing calculus are functions. So when we say calculus over complex numbers, what does that mean? It means that we are considering functions whose inputs and outputs are both complex numbers. Now, once you have these basic objects called functions, what does it mean to do calculus? What are the notions that you need? So you need the notions of limits, continuity, differentiation, integration, and sort of the pinnacle of all of that is this result that brings everything together, which is, in one variable, you know it as the fundamental theorem of calculus, but really this is just a particular avatar of Stokes' theorem, right? So Stokes' theorem is sort of what brings all of this together, and it has many, many consequences. So this course is going to go down that track. We are going to talk about complex valued functions with complex variables. We are going to talk about what does it mean to take limits? What does it mean to differentiate such a function? And just as in Math 221, you spent a considerable amount of time understanding the real number system, right? By which I mean the algebraic and the topological properties of real numbers. So we have to do that with complex numbers as well. Of course, our knowledge of the real number system really goes a long way. We don't have to spend as much time on complex numbers. And also the reason why this is important, so you may wonder why to do analysis, we need to understand certain algebraic properties of C. There are many answers to this, but one fundamental answer is that if you think about differentiation, so think about the first time somebody told you about a derivative, we always think of the derivative of a function at a point, giving us the information or sort of telling us the first order approximation of the function, right? It gives us a linear approximation of a function. So the same thing holds for complex derivatives. If I have a complex valued function, whatever that means, and I take a complex derivative, whatever that means, that complex derivative should give us some sort of first order approximation or linear approximation of the function we started with. And when you see the word linear, the point is that you have to understand this is an algebraic object, so we have to understand linearity in the sense of C and not in the sense of R. That is why these courses always start with what are the algebraic properties of the number system that you're working with. Okay. By the way, I'm going to keep getting some requests to join the team during the first class. So sorry for the interruption, but I should let these people in. Hopefully this will all get ironed out, by next week. A bunch of requests. So let me accept all these people so that we can move on. Another thing I want to say is because we are on a 1 hour time slot, I will always start sharp at 2. So please make sure that, everything will be recorded. So if you miss out something, that's fine, but just so that you know. All right, so So let's, as I said, let's do what I was saying, which is revisit the algebraic properties of C. I'm saying revisit because I believe many of you have seen this stuff. In fact, the first couple of classes may feel a bit like a recap, but it's still worth getting everybody on the same plane. So be patient if you've seen this before, but still be alert. And if you've not seen this before, please feel free to interrupt and ask me to slow down if anything is not clear. All right, so I'm going to switch to my tablet and hopefully more requests going on here. All right, after 5 minutes, I'm going to stop taking requests. It's a little late and it disturbs the class. Okay. So I hope everybody can see my screen. I have something already written there. Typically, at the beginning of every class, I might have a short recap, but everything will be done live, okay? I will also, even though I will post recordings, I will not post notes because I do want to encourage a habit of note taking. If you have missed a class for a very good reason, you may write to me and I'll send you the notes. But in general, I prefer that you take your own notes. And so I will be doing live writing. Any questions before we get started on this stuff? You know, it can be logistics or anything. This is just like a warm-up class, so please feel free.
Yeah.
Chinmay, go ahead.
Yeah, so you said about 221, but for us undergraduates, this is a core course and we haven't taken 221. So I mean, I think you might know that. So I was just letting you know.
Wait, what, wait. Okay, sorry. So, okay, first of all, this is my first year here, so I still don't fully understand your undergraduate structure.
Okay.
So are you not required to take 221?
No, so this is our core course of our third year, second semester. And we've taken an intro to analysis course as a core course of last year, but we have not taken 221.
No, but I'm pretty sure we've taken a course equivalent. I think the UM205 is equivalent to the MA221 course.
No,
Okay, I see what you guys are saying.
204 is not equivalent because 221 lists 204 as a prerequisite. So
yeah, so I checked the syllabi of UM221 and MA200. They're similar. They're almost the same as 221.
Okay. This is interesting because I actually spoke to a couple of UG coordinators and nobody pointed this out to me. You know what? It's okay. You don't have to register by today, right? Today is not the deadline. So let's just go along for the day and let me just figure out what's going on over here. So far, I don't think it affects anything that we're going to do today. But let me verify this. I'm a little worried now because a couple of people actually wrote to me and I somehow assumed that this was a course for third year UG students. Isn't this a core course for third year UG students?
Yes, we are third year UG.
Yes, so I somehow assumed that in your first semester, you would have done MA 221.
No, that is not a core. Maybe some people here have taken it, but that's not. I think most people.
No, I don't think anyone would have. Because
with Goody, with Tirupati Goody, you did not take analysis 1, real analysis?
Correct.
Interesting, because on the website, on the math website, it lists it as a core for UG third year. Oh God, okay, I'm sorry about this. I'm going to check. So let's not delay the class too much with this. I think it doesn't affect anything that we do today. I'm sorry about this. I somehow just followed the web page, and that seems to suggest that MA 221 is a core course for UG third.
I think that's a core course for first year in PhDs, and the UGs need to take UM204. I mean.
Okay, this explains a lot of the confusion that I was facing yesterday. All right, so if it's okay with you, let's just carry on today because I don't think we can sort this out within ourselves. If it's just up to me, then I think I'll take a look at your syllabus again, and then if you're saying that you've done a certain amount of equivalent material, I'll accept that. I think it should be up to me, but I'll just check again. I don't want this to become a problem at the end, right? So that's something that we need to be careful about. So I'll definitely get back to you about this today evening itself, but let's carry on for now, okay? Is that fine, Chinmay?
Yeah. Yes.
All right,
Yeah.
good. So, all right, so let's get to the math and sort this mess out in a bit. So we want to cover a little bit about what the complex number system is about, and I will constantly keep invoking this business about real numbers. So even if you've not seen a proper construction of the real numbers, which is what one does in MA 221, you know that you should know this fact that the real numbers with the standard addition and the standard multiplication of real numbers forms a field. And that means something. It means it has to satisfy certain requirements. So let me kind of remind you what those requirements are. First of all, real numbers have to be closed under these two operations of addition and multiplication. Secondly, the order in which you do these operations do not matter. That is commutativity. That's the second point. The third is that you typically want to iterate these operations. And once again, the order in which you iterate these operations don't matter. That's associativity. There is an interaction, an expected interaction between the two operations. You know this as the distributive law, and we kind of almost blindly do it with real numbers. That is a field axiom. And what a field needs to have, it has to have for each operation an identity element. So we call the additive identity 0 and we call the multiplicative identity 1. And what they do is under the operation, they have no effect on a real number. And finally, for both addition and multiplication, every number must have an additive, every real number must have an additive inverse, which we denote by minus of that number. And every non-zero real number must have a multiplicative inverse, which we denote by x to the x to the power minus 1 or 1 over x. So now, and the real number, the real number system as a field, it also admits an order. And it's a nice ordered field in that it has the least upper bound property and things like that, which are quite useful to have. However, there's something missing in the field of real numbers, so it is not algebraically closed. So R is, oops, I want to use white. So R is not algebraically closed. So there, for example, you have the simple polynomial x squared plus 1 equal to 0 that does not admit any solutions in R. So you know this as negative numbers have no square roots, have no real square roots, so it does not admit solutions in R. So formally, if you want to understand complex numbers, formally C is the algebraic closure of R, but in other words is the field, the extension field. It's an algebraic extension field. Ri, which is that I am formally adjoining an element that does what I want to do, but there is a more concrete way of obtaining this, which is that you take the field of polynomials with real coefficients and you quotient it out by the relation that x squared plus 1 is equal to 0. So you're sort of artificially adding a square root of minus 1, and that actually goes a long way in adding many other things, other square roots of other negative numbers and stuff like that. But this is a definition that's not the most useful from the point of view of analysis. So what we will need are more concrete representations of C. Where are my notes? Okay, so let's kind of go to that. So for most of this course, what we are going to worry about is, or what we're going to think of C as, we're going to identify it with, so we are going to identify complex numbers with two-dimensional real vectors or ordered pairs of real. And I need to tell you what I mean by multiplication and addition over here. So one is the Cartesian. We'll use Cartesian coordinates. And here, so if I denote my complex numbers as real vectors, I'll typically use the notation z equal to x comma y and w equal to u comma v. Okay, so the addition part is, so let's use I. So z plus w, we just do standard vector addition. So this is just component wise, which you also know what this does geometrically. So if Z is represented by this vector over here and W is represented by this vector in the plane, so this is R2 over here, how do I represent Z plus W? So I take the parallelogram generated by these two sides and I take the diagonal emerging from the origin, and this represents the vector Z plus W. And for multiplication, it's more useful for me to tell you the following two things. So the vector 1, 0 is going to act as our identity. So when it acts on the vector W, you just get back W. But the more interesting property is the one that comes from multiplying a vector by 0, 1. And what that does is it rotates your vector counterclockwise by 90 degrees. Okay, and telling you is actually enough to tell you what multiplication means in this sense. So we'll come to that. So let's say this is my vector. Okay, let's stick to the old vector W. So this is W over here. And when I do 0, 1, this is, let's say this is 0, 1 times W. Okay, so I've just rotated this counterclockwise by 90 degrees. All right, so why did I say that this suffices to figure out what multiplication looks like? Because now if you look at Z dot W, you can sort of use linearity over here. So this just becomes X times 1, 0 plus Y times 0, 1. I'm multiplying this with U, V. And I kind of do this kind of use a distributive law. So I get X times UV plus Y times minus V, U. And that just gives me XU minus VY, XV plus UY. Okay. So really the key thing over here, the geometric thing going on over here is this particular multiplication that I mentioned at the beginning. All right. Why does my screen look stuck? All right. So a couple of things for us to check, which I leave to you. I feel like you have seen some of this stuff before. So check that these operations satisfy the axioms, the field axioms mentioned above. The way we have defined them. So you have to find your identity elements, you have to find your inverses and things like that. But one thing to note over here that we will use, note that the map which sends X to X, 0 is a homomorphism from R into C. So we will often, use this real line sitting inside the complex plane. We will often use that. All right. So what this notation kind of gets tedious after a while. So what we'll do is we'll modify this notation a little bit, and we'll note that it is convenient to write the vector 1, 0 as 1 and the vector 0, 1 as I. So this Z, which I was calling X, Y, really just becomes X plus IY, which is the notation that you might be familiar with for complex numbers. So here, just to put all the terminology, X denotes, or X is the real part. It's called the real part of Z, denoted by real Z. And similarly, Y is the imaginary part of Z, denoted by IMZ. Okay. And the convenience of this notation is that, things get a little bit quicker. So let's do the following. In this notation, even though this is technically a little exercise that I have left for you, in this notation, let me at least compute the multiplicative inverses of non-zero numbers. Okay, so it should be clear to you that 0 plus I0 is the additive inverse, because addition is just the traditional addition of vectors. So in this notation, say C plus ID is acting as the multiplicative inverse of, I'm kind of terrible at staying consistent with notation, but I'm going to try my very best. Okay, so please point out if you see me kind of being inconsistent with notation, don't hesitate to interrupt. But I want to say, so I want to start with something which is a non-zero number, complex number, and I want to compute its multiplicative inverse. Then what does that mean? It means I basically just need to solve two equations. So I need to first solve a complex equation that looks like this. But a couple of minutes ago, I told you what this product should be. So we've discussed that this product should be the following pair, and this should be 1, 0. So you sort of solve these two equations, which we are not going to do here. And what you get is that x plus iy inverse simply becomes x minus iy divided by x squared plus y squared, which is all fine because we've assumed that x comma y is not 0, 0. All right, so the reason why I did this short exercise is because now this gives me an excuse to introduce two very important objects over here. One is what you see in the numerator. So this is the conjugate of so given a complex number z, so how do we write this? Okay, so given z x plus iy in C, the conjugate of z, z bar is x minus iy, which again, since everything can be viewed on the two-dimensional plane, it's worth asking what this is doing to a vector. Well, what this is doing is that it's reflecting the vector about the x-axis. So if this vector is z over here, then z bar is this reflection. And the seemingly innocuous object is actually very useful. That's why we denote it by, we give it a special name. And for instance, one thing you can do is, this is easy to check, that you can write your real and imaginary parts now in terms of z and z bar. So this helps us go between the real and the complex notation a lot of times. And it has a lot of algebraic value being able to do this. Okay, and the second object that I want to talk about is coming from the denominator. So this is the conjugate of z. So this is one definition. And given any z in C, the absolute value or modulus of z is absolute z given by, so I'll first tell you what absolute z square is. It's a real number given by z times z conjugate. And if you actually do this multiplication, you basically get x squared plus y squared, which is a non-negative number. So I can take its square root in the sense of real numbers, and that gives me absolute value of z. And again, pictorially, what it is just the length or the magnitude of this vector over here. This is absolute z. Okay. Now, we are allowed to call this absolute value of z or modulus of z because if z is real, remember that R is sitting inside C. By the way, I just, a couple of minutes we discussed that a couple of minutes ago. So if Z is in fact a real number, then this notion coincides with the notion for real numbers. So we are allowed to use this terminology. Okay, so some properties that will be quite useful down the line, some properties of this absolute value function. So I'm already calling it a function, but I haven't really gone into, what is continuity? Is it a continuous function of complex numbers, so on and so forth? We'll come to that. But some simple to check properties is that since taking a conjugate is basically reflecting a vector, the magnitude of the vector is not really going to change, right? If you take absolute value. And so this is something that needs a little bit of computation, but absolute value of z times w is the same thing as absolute z times absolute w. And then something that will be tremendously useful is the triangle inequality. And what this says that for all pairs of complex numbers z comma w, the following inequality holds, that if you take the absolute value of z plus w, then this is at most absolute value of z plus absolute value of w. And typically when you write down inequalities, it is also worth trying to figure out when this inequality becomes an equality. And so this is something is worth knowing, and equality holds if and only if when I look at the product ZW conjugate, which is a priori a complex number. This in fact must be a real number, and in fact it must be a non-negative real number. That is when this inequality becomes a proper equality, okay, or a proper identity. So let's go ahead and do a proof of this, because today's class being somewhat of a recap, we are not really going to do many proofs. But since it's warm up, and since any self-respecting analysis class must have some inequalities, let's just go ahead and do this. So anytime you want to work with the absolute value, it's almost always a good idea to work with the square, because it's much easier to work with. So what you have is z plus w times the conjugate of z plus w, but the conjugate is linear over addition. So I can write this as z conjugate plus w conjugate. Wait, let me make sure I see a chat message. There is a question over here. Sorry to interrupt, but modulus is actually extending the notion of modulus of real number, but absolute z equal to absolute x plus absolute y also does that. Why don't we use that? Right, so in some sense, yes, we are making a choice. You're right that they can be, I mean, this is not, the extension of this function is not unique. And what we have done is that what you are, so if you think about, okay, so let me, so this question is in the chat box, and the question is that there are other ways of extending the modulus from R to complex numbers. I've never really thought about this, but my instinct is that, first of all, when you identify, maybe this is not well defined. I suppose the suggestion, so when you say well defined, one is really just asking. So it depends on what you're asking for the modulus function. Right? If you're just asking for a real valued function from C to R, which extends the notion of modulus from R to R, then what Bapa has suggested is completely fine. It is extending the function. But the question is that what do we want out of the modulus? Okay. Sorry. So, Meghal, did you want to say something?
No, I just I don't know what he means, but if he says z equals x plus y, then z can be written as a sum of multiple things, and then all those would give different moduli.
But I think he really means that z is x plus iy, so its representation as x plus iy is unique.
Oh, okay, fair enough.
Does that make sense?
Yeah.
So when he says z is equal to absolute x plus absolute y, I think he means So he means absolute part of real Z plus absolute Y of imaginary Z. Okay. So it is well defined in that sense, but it's more to do with what are we doing with this absolute, what do we need from this modulus? And the point is that you'll see down the line that, so one of the things is that currently the way I have defined modularity or modulus, it sort of respects multiplication, right? So absolute ZW is so absolute value of ZW is absolute Z times absolute W. Whereas what you have defined over here is not going to do that. And one thing that I want to actually, yeah, so you still have your triangle inequality. And I'm sort of trying to think about what it is that will really break down over here. So you'll definitely still have triangle inequality. There's a raised hand. Does somebody want to say something at this stage? Nikhesh?
No, actually, I wanted to say that when we look at the metric space structure, that absolute x plus absolute y is a taxi cab metric. So it doesn't give the required length Euclidean metric on the complex numbers. Maybe that's why we can't extend the modulus.
Good, yes. Right. So the point is that exactly. So I think like in some sense, and Shekhar also wants to say something. So let me allow Shekhar to say something before I wrap up this point.
Well, what I had in mind is slightly different. Essentially, if we are looking at complex numbers as a isomorphic space to R2, then the notion of modulus that we are sticking with makes sense, right? Because that translates to the normal norm in your R2. Secondly, and this is a slightly existential question, if complex numbers can entirely be treated as R2, why are we learning complex analysis? Why not Rn analysis directly?
Good. So all good points and all good questions. So first, let me summarize sort of the first point that Shekhar made, and I think this is also Nikhesh's point. And I want to say that Bapa's question is legitimate in that he has given me a well-defined function from C to R, which extends the notion of modulus. It does satisfy the triangle inequality. So one can continue this course with taking that as the metric. So there is no issue with that per se, but our experience, so there is a reason why one studies complex analysis. It seems to complex functions come up naturally. And it seems that what we really need, so just because C is isomorphic to R as a field, that doesn't say anything about them as metric spaces. We want them to match also as metric spaces where we understand R2 in the traditional sense with the traditional Euclidean metric. Okay, so in some sense, the extension that we wanted of the modulus function, we wanted to coincide with the notion of distance that we have on R2. Yes, it is a choice that we are making, but that choice is for a reason because we want that metric space to work with. Okay, so what are the flaws of the metric space that Bapa has suggested? I don't fully know, and I don't know how much of a calculus you can develop going down the line with that metric. Something to think about. Now, Shekhar's question about if everything that we are doing is basically making C seem like R2, then what is going on over here? And that is going to become a little bit more clear when I define holomorphicity, because while we are identifying C with R2, our notion of what is linear, that there will be two different notions of linearity. There is something called R linearity, or linearity in the sense of real numbers, versus C linearity. So as vector spaces, I'm treating them as vector spaces on two different fields. I'm treating R2 as a vector space on R. I'm treating C as a vector space on C. Okay, that is the key difference over here. Any other comments regarding this discussion? Anything? Anybody has any? Anybody wants to say anything? All right. If not, so let's carry on. And there is still this question: what would happen if we actually developed this discussion based on this absolute x plus absolute y metric? Okay, something to think about. All right. So let's continue the triangle inequality. Now you already know why I'm trying to prove this, because we want to set up a metric using this. So as I said, you kind of just go by definition. You sort of distribute over here, and you get absolute z square plus absolute w square plus 2 times real value of zw conjugate. Now you use the fact, there is a message again. Sure, Papa, yeah. All right. So, so now what you do is you use the fact, and this is something that you need to think about, but you can also sort of visually see why this is the case, that the real part of any complex number is always less than or equal to the absolute value of that complex number. Okay. And so what you get is now you switch to an inequality, and it's always good to keep track of when you're switching to an inequality. That's often the key point. And here, this inequality switches to 2 times absolute z, absolute w. And now this is nothing but absolute z plus absolute w whole square. Right? By the way, continuity with respect to Bapa's definition implies continuity with respect to our definition. That is what triangle inequality is saying after all, right? Yes, Agnik, it is true that the multiplicative identity will not hold with the definition that Baba has suggested. So certainly some changes will occur, and it's something to wonder how it will affect the geometry of it can be develop a calculus based on that. Okay, so I'm going to sort of end that discussion here so that we can move on. I'm sorry, I think I have been interrupted. Okay. I'll try to be in the department from next time onwards. The connection is poor here. All right, so we're almost done over here. Now this inequality from the first point to the last point is within the realm of real numbers. So this implies that absolute z is at most absolute z plus w is at most absolute z plus absolute w, where equality holds if and only if. So really when it became inequality, it was really only at this stage. So you can see that what we are saying is that this would not be a problem. We would not have to use an inequality sign if real ZW bar was in fact absolute ZW bar, but real part of Z is equal to the absolute value if and only if ZW itself is CW bar itself is a non-negative real number. So the second part is not that hard to see. Okay, and now this tells you that something that we will talk a little bit more about next time is that if I define my distance function absolute z minus w, this is a metric on C. And of course, we've already had a long discussion that this is exactly the metric that we do consider on R2. So that's somehow comforting at this stage. And somehow equally useful is the reverse triangle inequality, which really is just a corollary of the triangle inequality. So I'll leave it for you to think about and do write a proof down. So for all pairs of complex numbers, if I now look at absolute z minus absolute w, this could be a positive or negative number. I'll take the absolute value. This is at most absolute value of z minus w. Okay, so your short exercise over here is prove and also characterize when equality holds. So characterize the pairs of complex numbers for which equality holds above. So when does triangle inequality become an identity? All right. So so now this kind of brings us to another point. I think I may have lost you for a minute. All right. Okay. So let's kind of discuss. Hopefully I'm back. Connected
Yes,
again.
Yeah, we can hear you.
Okay. All right. So, once we've done this identification with R2, you know that it's also quite useful to actually use polar coordinates, especially for complex numbers. And this will also maybe answer that question about absolute Z a little bit more. So remember that, so given Z in C star, so I'll use this notation a lot, which is basically C minus the origin, or C minus the zero. Okay, this C star I'll use a lot. So given a non-zero complex number, the argument of Z is what, which I'll denote by arg Z, is the angle. And you know, in this course, we will always measure angles in radians. So measured in radians. So the angle that the vector Z makes with the positive x-axis. So this is a geometric definition. And pictorially, this is arg Z over here. So this is my x-axis, this is my vector Z. Now, of course, this is not uniquely defined. This is uniquely defined up to an integer multiple of 2 pi. And so we have to make a choice. Since this is not unique, we make a choice. And this is actually what is known as a branch. Okay, we make a choice of branch as follows. And how do we make this choice? So I'm going to define arg Z. And again, whenever I write Z, the implicit understanding is that Z is X plus IY. Okay. So so how do we define arg Z? To give it a fixed choice, I'll define it as arctan of Y over X when the imaginary part of Y is either non-zero, or if it is zero, then we are on the positive x-axis. And then I define it as pi when both on the negative x-axis. Okay. Of course, Z, this argument is not defined when Z is 0. All right. So setting absolute Z as R and arg Z as theta, we have that I can write Z, which is X plus IY. I can write this as R cos theta plus I sine theta, where I'll write it like this. Right, so this is our polar. Should that be imaginary Z rather than imaginary? Yes, of course. Thank you. Oops, why is it not erasing now? Yes, okay. Yes, of course. Thanks. Right. So now this is useful. You can see that the absolute value of Z, the way we have defined it, is playing a very important role. And polar coordinates are kind of the reason why people always introduce this at the very beginning of a complex analysis course is because they kind of justify the weird multiplication we were doing in the beginning, right? So we introduced this multiplication which seemed quite artificial, but now if I express multiplication in terms of polar coordinates, things become a little bit more clear. So I'll take two. Sometimes you'll also see me write r comma theta. I won't do this very often in the course, but I might do that. Not a big fan of that notation, but okay. So let's stick to what I have right now. So I'll take two complex numbers, and of course, assuming they're non-zero, and I'll take their polar coordinate representation, S times sine phi. Then if I take Z times W, what this becomes Rs times Now you get cos theta, cos phi, minus sin theta, sin phi, comma, or rather plus I times cos theta, whoa, what's this? Cos theta sin phi plus sin theta cos phi. Okay, this is just by the rule for multiplication I gave earlier. And now using some trig laws that I hope you've seen at some point of time, all this becomes Rs times cos theta plus phi plus I sin theta minus phi. Oops, theta plus phi. All right. Okay. So what this is saying, this is telling us, so we already knew that if the modulus of the product is the product of the modulus, but now we are also saying that the argument of the product is the sum of the argument. Okay. So this is giving us some sort of a visual handle on what multiplication really is doing. So let me say that verbally and also represent it here. If you have two vectors z and w, then, and let's say the angle of z is theta here and this is phi. And let's assume for the moment, for the sake of this picture, that z is a unit vector. Okay, so its length is 1. And so when I multiply, what is the effect of multiplying w on z? What does it do to z? It first of all rotates z. So it rotates z so that the new angle becomes theta plus phi. And it multiplies the modulus of z by the modulus of w. So in this picture, it will just look like this. So multiplication has the effect of dilation plus rotation. By dilation, I just mean scaling. So this has a very nice geometric interpretation. And then what this allows us to do, this kind of polar representation, apart from making this interesting point, which is going to keep coming up, it also makes it very easy for us to take integer powers. Okay. Also, I think these are known as de Moivre's laws. So I'm assuming some knowledge of trigonometry, but these are all, you can look up these things. If you're not familiar with them, just look them up. What you get is that z to the n, which a priori is r cos theta plus I sin theta. Okay. R cos theta plus I r sin theta to the power n. This becomes nothing but r to the n cos n theta plus I sin n theta. Okay. By the way, when I do n times theta, the argument may exceed what is the accepted value. So I didn't quite explicitly write this down, and maybe I should have written this down. So let's do that. Let's go ahead and fix the issue. So the way I have made a choice, I have forced the argument of a complex number to be between minus pi and pi, where I'm including pi. Remember, arctan stands for a very specific choice of the inverse of the tan function. Okay. So even though I'm saying the argument has to be between minus pi and pi, if you multiply something by n, it could exceed pi. And then the point is you kind of view this modulo this interval. So you always bring it back by subtracting enough number of 2 pi's, you bring it back to the correct interval. That's how you should interpret these things. Anyway, yes, Shekhar, go ahead.
I may be mistaken here. If could you go back to the definition of argument once?
Yes.
Doesn't arctan typically reside in minus pi by 2 to pi by 2?
No. So, you are right. So I am missing something over here.
This could be a pi plus something term, if I'm not wrong.
Yeah. So the way I want to do this is kind of maybe I should do it the following way. So the way I want to do this is, but I don't want to do a plus over here. So why did I write it like this? Let's think about this. So we are in the positive quadrant. I want to go from 0 to pi over 2. I can probably fix it the following way, right? I can probably do something like 2 arctan y over 2x. If I do it that way, let's see. So yeah, this is a little annoying because now I have to define it in this piecewise manner. Let's see. So, oh, there is a Prashant. Do you want to say something?
I think we need to add the conditions where x is equal to 0 also, and then piecewise we have two more pieces that way for pi by 2 and minus pi by 2.
Yeah, that's what I was wondering. So that's a good point. So now this has to be like 4 pieces, right? So in each quadrant, I suppose this part is fine, right? This piece is fine. The right hand side is fine. And then, okay, so let's fix this. Thanks for pointing this out. Let me make this small. Okay, so how do we do this? So my worry is that how do I actually, then I have to artificially define it for x equal to 0 as pi over 2 when, okay, at least for the sake of these notes, I'm sure there is a more efficient way of doing this, but at least for the sake of these notes, let's do it as follows. So let's artificially define it as imaginary part of z is positive, real part of z is 0, minus pi over 2, imaginary part of z is negative, real part of z is 0. Now, but arctan is still from minus pi over 2 to pi over 2. So for the rest of it, how do we do this? So we do so let's see. So if we are here, what do you think should be the solution on the left-hand side? We still have a piece missing, right? So we've only figured out what we had on the right hand of the plane. We still need to figure out what's happening on the left hand of the plane. So let's see, we are here.
You can just add pi, right?
Yeah, I think it might just be a good idea to do pi plus arctan y over x. I'm always concerned that we are doing something wrong over here. This is for otherwise. So here this is, maybe it's best to put it down here.
If we do it this way, we will get the value from minus pi by 2 to 3 pi by 2. I think.
So currently we are at pi over 2. Now you're saying that if I take, so let's say we want to take something like this, right? We want to take arctan of y over x. No, it seems fine to me, right? So you'll get arctan of a, so let's say we are here, you'll get arctan of a negative number. You'll be between minus pi over 2 and 0.
But quadrant be more problems.
There must be a way to define this, which I'm...
If I may, maybe
Yes,
using cos inverse is a better idea here.
Because it gives you a better range.
Plus lesser exceptions.
Okay, fine. So let's do the following. Okay, it's close to, okay. So rather than try to struggle with this over here right now, can't believe that the error is a trigonometric problem over here. So let me delete this. We still have to worry about exceptions because we still have to take a worry about, like, we'll probably have to do something like arc cos, and then we have to do x over absolute z, I suppose, right?
Arc cot might be convenient for this.
Okay. Okay, I don't think that at the end of the class we should be figuring this out on the spot. So let's fill in the gaps next time. I'll fit this into the piece before I sort of start again next time. Let me just finish this point. So next time we'll kind of start from here. Finish this discussion plus some metric or topological properties of. Okay, so next time I'll give you a consistent way of writing your argument function. It's going to be one of these things you just have to figure out, ideally we would like to keep our argument between minus pi and pi. That's just a convention, and next time I'll just tell you what is the most consistent way of doing it. Certainly the way I'd written it was not working. So thanks for pointing that out. Let me stop here for the day, fill in this gap later. If there are any quick questions, please go ahead and ask right now. If not, yes, Shekhar, go ahead.
So about the cos inverse thing.
Yes,
If
yes.
we're using absolute value of z in our denominator,
Yes.
then for any value of z where you can define an argument, there is no situation where the denominator can be 0.
Right. So it does. You're right in saying that. I do think that you're right in saying that the exceptions, we don't need exceptions for that case. So our cos might be a good candidate. Yeah.
Yeah.
But then remember that we are going from 0 to 2 pi.
Not really. Our cos lies between 0 to pi, and then for the third and fourth
So you
quadrants, we
still
just
have
add.
to. Yeah. Okay. Fine. We can. No. Well, I mean, you can define it from minus pi to pi, right?
True.
Yeah. So that's not an issue. I think it's just a matter of taking your choice of, you can use any choice of arc, whichever trigonometric function you want, you just have to shift it correctly. So the one I had in my notes, I hadn't thought it through correctly, but if you just fool around with it, you will get the right format. But I'll kind of not try to do it in a rush right now. I'll just add it in later. There is a comment as well. Let me just take that comment. So somebody has suggested the way to fix arctan, and so we can check whether that is true or not. But again, maybe, so let's see. Arctan y over x, second quadrant is plus pi, last quadrant is minus pi. Okay, I think that should also. Yeah, that does sound right to me. Okay, anyway, as I said, let's fill in. I'll leave this gap over here, fill it in, and then we'll continue from there. Any other questions?
So about the one very well-known result that we use, e to the I theta kind of stuff.
Correct.
Do we go into that in this course?
Yes. So the point is that I haven't really told you what it means for, what does it mean? What does e to the z mean? So we will be talking about that. And once we do that, the next couple of classes, so I'll introduce functions on the plane, and then e to the z is a very important function, but what does it really mean, because we understand e to the x. So once we have that, we can write this in a more compact form. Okay, I'm guessing that's where you're going with this.
Yes.
Yes, we will come to that. Absolutely.
All right. Thank you, ma'am.
Sure. All right, so one thing I have to do for you before we end class is I need to check for the undergrads what the real matter is. And if everything is fine, then I also need to tell a couple of people. I've already said no to a couple of people, so I'll make sure that they are able to log in. All right, so that's it for today. You can log out. We'll meet on Wednesday. And in the meantime, watch out for my email or message or something. All right, so we'll end class here. I'll hang out for a couple of minutes if anybody has any questions, but feel free to log out if you're done.
Thank you, ma'am.
Thank you, ma'am.
Sure.